Hey, physicists. I hope you're having a great snow day. I am kind of surprised that we're not in school today, but that's okay. We are here together via the beauty of technology. Of course, on this snow day, I forgot to bring my stylus to school, or home from school. So I'm going to do everything kind of by typing it out, which is why it took me a little longer to get it all ready for you. Anyway, let's jump in and get started. So yesterday, when we were together, we were talking about moment of inertia and we had defined it at the end. We worked on a problem together, but I just wanted to reiterate a couple of things to make sure that it made sense to you. So, first of all, just a reminder of what the phrase moment of inertia means. It's not intended to be scary at all. It's really just an object, so that means apostrophe. There we go. Object's resistance to rotational acceleration. So, one way that's kind of nice to think about that is to relate it again to the whole idea of translational versus rotational. So remember that we said in translational motion, if we have the same net force as mass increases, linear acceleration decreases. It's harder to get something to accelerate, right? We're saying the exact same thing for rotational here. It's just that now we're using different words. So given the same net torque, as the moment of inertia goes up, the rotational acceleration decreases. So it's the same kind of concept. Mass A change in mass gives you a change in linear acceleration. A change in moment of inertia gives you a change in rotational acceleration. So hopefully that makes sense, and we're going to work on some problems here that will help to kind of reiterate that as well. Okay, so just a couple of pieces of information that would be helpful probably to write down. Remember, we derived yesterday that in general, for a point mass, I, the moment of inertia, is equal to m times r squared. So m is the mass of the object, and r squared, r is the distance that that mass is from the axis of rotation. Okay, so remember the problem from yesterday with the bar and the unequal distribution of mass, depending on which side of that bar you were holding on to, the moment of inertia changed. So it's the distance r is the distance from the axis of rotation. You square it because the distance matters a lot. So that's all well and good. We're going to, like I said, get into some more problems here. And there's a note that is important to have. So if there are multiple masses, instead of just knowing the total mass, you need to find the sum of all of the moments of inertia for the whole object so that you can figure out how that moment of inertia is going to impact the rotation. Okay, so it says here, and I'll just reiterate for you that for translational motion, it's only the mass that matters, right? So if you got a little boulder versus a big boulder given the same force, the acceleration just depends on the mass of the boulder. For rotation, it's not just the mass, but it's also the distribution of the mass that matters. Okay, so write that down, kind of start to internalize that because that's the key difference here between translational and rotational motion when it comes to Newton's second law. Okay, so on Canvas, there are three problems for you to work. Actually, the bar that we worked on yesterday, the one that looks like this, is the first one in the sheet. You can skip that one or you can make notes on that one if you'd like as well. But there are two other problems that I'd like you to work on. So I'm going to ask you to pause the video now, okay, to work on those problems. One's a ranking task and one is a calculation problem. Work on one, come back to the video, check your answers, and then work on the other one. Okay. I put on here because I really want to make sure you know it. I don't want you to just rely on the video for the answers. It does require engagement in order to learn this physics. Okay. So go ahead and pause the video, work on problem one, and then hit go when you're ready to come back. All right, so hopefully you're ready to come back. Hopefully you took a little time to work on this problem. So this one is the one where you've got your multiple masses. It looks kind of like a jack. I don't know if you guys ever played jacks when you were kids, where you bounce the ball and then you pick up those things. So this is a jack, but it's got multiple different masses, so different distributions of mass. And it asks you in this first problem to rank the moment of inertia about the x-axis. So you are taking all of those masses, finding the moment of inertia of each of those, and then finding the sum of those masses together. Okay, once you've done that, let's take a look at what the answer is. So it asks, the answer is ranked D is greater than B equals C is greater than A. Okay, Once you've done that, once that makes sense to you, then I'm going to add a second problem in there, and that is where it says x-axis, change that to y-axis. So now instead of rotating it about that axis that's kind of coming out of the page, I want you to rotate it about the axis that's labeled y. Go ahead and see if you can do that. And once you've got it, then hit play again and we can check your answer. All right, so hopefully you've taken a look at that. So here is the answer to that question. If it's not making sense, then let me know. We can certainly talk about it. But all you're doing, friends, is to take those moment of inertias for each of those pieces and then add them together. Make a note of it. Send me an email if you need help. I really want to help you out with this. Um, but I want you to engage with it and not just rely on me to tell you the answers. Okay. Once you've got that, then go ahead and take a look at question 3. Question 3 looks like this. Okay, so hopefully you've paused it, you've worked on the problem. The answers are here for you to check. Again, it's all about finding the sum of the moments of inertia. The game here is that you've got the same object, right? But we're changing the axis of rotation. So in part A, the axis of rotation is vertical and it's going through this piece of abstract art so that the object is going to rotate around, kind of making like a bowl shape, I guess, and a square bowl. Whereas in B, the axis, you can see it says coming out of the page. So it's like if you put your pencil up to the screen, it's coming out of the page and it's rotating around that way. Just because of the change of axis, again, the same mass, but a different distribution of mass relative to the axis of rotation. And that's what's changing the moment of inertia. One thing to note in part B, if you didn't catch it, is that the distance here for M3 has to be the hypotenuse of this triangle. So you need to do 10 centimeters squared, 10 centimeters squared, square root it, right? And then find that in terms of meters. I found all of my answers in terms of meters. Okay. Now, last one that I'd like you to work is question 4. Question 4 is a little bit interesting, so go ahead and take a look at that one. Once you've got that, then we will come back and chat. All right. So hopefully you've had a chance to look at question 4. This one's a little different, right? So now we're looking at not just point masses, but we're looking at mass that is distributed all around an axis. So this one's a little bit different, and I really wish that we could chat about this as a group, but since we're all sitting at home in our PJs, it's harder to do that. So let's just kind of talk it through this way. So in each of these cases, in A, B, and C, there's the same amount of mass, but again, it's just the distribution that's different, right? So we remember that the moment of inertia is dependent on both the mass and the distribution. If we look at A and B, a has all of its mass all the way on the outside of the circle, whereas B has a lot of its mass in the middle. So if you have IR squared, right, and we take a little bit here and a little bit here and a little bit here, and we add all of those up, hopefully it makes sense to you that the moment of inertia for B is going to be smaller than it is for A, where all the mass is located outside on the outside of the circle. Okay, so the moment of inertia for B is less than the moment of inertia for A because more of the mass is closer in, so the R's would be smaller. All we're doing is adding up little bits. For my calculus friends, we're really just doing an integral. That's where all of the stuff comes from. Okay, you don't need to be scared by that if that's not something you know what that means, but it's okay. I just want to throw those words in there for our friends that know. Okay, if you take a look at C, C and A look very similar, but C spreads out just a little bit over here, which means that there's a little bit more mass way out here, further away from the axis of rotation than it is in A. And as a result, C has a bigger moment of inertia than does A. So the answer for moment of inertia question 6, or excuse me, question 4, I apologize, should be C is greater than A is greater than B. So I like this question because it kind of leads from adding all the little bits together to a bigger picture. And that bigger picture then is available for you on the second sheet that I posted up on Canvas. Okay. And that is right here. So this is a kind of set of different um, objects about different axis of rotations and the moments of inertia of each of those objects. Okay. In the calculus based physics course that exists, but we don't teach at Liberty, we actually go through and write out how to do this because, again, like I said just a moment ago, it's all based on calculus. You do not have to have these memorized. You do not have to have them, like, you don't have to understand exactly where they come from. The things that I would tell you is to know are that just like we did in the problems before, like I'm going to go back to this one here, where we added up all the pieces and then the mass times the radius squared, that's exactly what's happening in each of these. We're just doing it little bit by little bit. And the other thing to know is to be familiar with the fact that the moment of inertia in each of those cases is very different. Okay. In a problem that you would work on an exam or on a test or homework or anything like that, you would have access to this equation, or it would ask you to figure, well, it probably wouldn't even ask you to figure it out. Just like, here is the moment of inertia for example, a solid sphere rotating about its um, diameter. Okay, and notice that the moment of inertia here is 2/5 mr squared. Okay, so then you would use that in the problems that you're working. All right, so I wanted you to be familiar with that. We'll work with this kind of as we go through this chapter, but that will you'll always have access to that or to something like that, those equations. Okay. Once you've gone through that, then the only other thing that I would ask that you do before I see you on Valentine's Day is to work these 3 problems. So I also posted these 3 problems up on Canvas. They are posted on the same page as the chart of moments of inertia. Give them a shot. I will try and post solutions, like actual written out solutions to them today, though I don't have my stylus, so I'm not sure if I'll be able to do that. If not, I will certainly put solutions up on Friday. Okay. If you have any questions before I see you tomorrow, let me know. Otherwise, I will look forward to seeing you on Valentine's Day. Have a great day, you guys. Stay warm. Bye.